But today we're going to be talking about sulfur. So it's a major element, part of the very common in the Earth's crust. It's got many chemical forms. It's got gaseous forms and solid forms. And actually, in some cases, there are liquid forms at the Earth's surface in terms of molten sulfur, which is quite hazardous. It also forms kind of molecules like hydrogen sulfide, which not only smell quite a lot, but are also kind of relevant to affecting kind of other element cycles. Okay? So it's produced naturally by things like volcanoes and that give off lots of sulfur gases. You can see here some nice sunsets that are caused by volcanic eruptions and the sulfate aerosols that they give out. But it's also kind of geologically, so you get deposits of gypsum and pyrite here. Okay, and these deposits quite actively mined, particularly gypsum for things like the building industry. Plasterboards are made of that. But also sulfur is, because it's involved in kind of biological cycling, so organic matter has sulfur in it, which means that fossil fuels quite often have sulfur in them. So when we extract and burn those fossil fuels, we're also emitting sulfur into the atmosphere. So there's an anthropogenic component to the sulfur cycle as well. Okay, so just like with all of the other nutrient cycles, we're going to go over and describe the stocks. We're going to go to the land, the ocean, and then some of the kind of implications. In this case, we're going to look at some of the interactions between the nutrient cycles, particularly acid rain. Just a bit of a heads up. So we're sulfur. It's one of these kind of like words that's got kind of like Americanized. So the correct spelling, of course, is the British way with a PH. The incorrect way is this ridiculous thing with an F in it. But because kind of America is currently winning at science, in the scientific literature, it should almost always be written as sulfur with an F. Okay, so you'll see it written quite a lot as this. Don't get so angry as I do. I mean, when you're writing stuff in the exam, I don't really care. Older members of the department may care more, but I don't. Just like so sulfur is important because it's an important part of quite a lot of the molecules that make up our cells. Okay, so again, amino acids quite often have a sulfur on them. Okay, apart from being kind of involved in being essential for life. Okay, but it also is a main source of acid rain. Okay, so when sulfate gets into the atmosphere, that reacts with water to form sulfuric acid, which is an acid, and that is coming from fossil fuel burning. Okay, so it also has a feedback on the carbon cycle through climate. Okay, so it has an effect on the temperature of the Earth through this cooling effect, which we kind of covered in the climate lecture series. Okay. So just to summarize the stocks of sulfur compared to all of the other things we've been looking at. The carbon and the nitrogen cycle sometimes referred to as the gaseous cycles because they have a significant component that goes to the atmosphere. So sulfur does have some atmospheric component, but most of the sulfur in the kind of the biologically active part of the world is in the ocean. Okay, so there's huge amounts of sulfur in the ocean. Okay, but then again, also large stocks in the sedimentary environment. Okay, so I guess one of the reasons why there is so much sulfur in the ocean, although it's a key nutrient, so life needs sulfur, but when life happens, it almost always runs out of nitrogen or phosphate first, so sulfur never gets used up. So it always gets left behind in the ocean. Okay, and it's very soluble, so that allows it to build up into large concentrations. And we'll come on to that in a little bit more detail. But the ocean is where most of it is. Okay, so some of the forms. So sulfur has got quite a complex chemistry. There's lots of different forms, and particularly lots of different oxidation states. So we have the oxidized form, sulfate, okay, which is here, which is the most common form of sulfur, particularly in the hydrosphere, so in the ocean, in lakes and rivers, stuff like that. And then we have reduced forms of sulfur, so pyrite in rocks which have basically formed under anoxic conditions. So those are kind of quite a lot of igneous rocks might have little bits of pyrite in them, but also sedimentary rocks formed in oxygen-poor conditions. So at the bottom of the sea, in the sediments, quite often starved of oxygen because organic material is respiring and using up all of the oxygen, so that leaves the sediments ultimately depleted in oxygen, which allows the oxidation state to be more reduced, leading to pyrite formation, so sulfur in the reduced form. But we also have some of these gaseous species. So sulfur in the reduced form in sediments, hydrogen sulfide up there is important because it can then get out of the sediment and then oxidize back to sulfate, which becomes acidic. But there are also these kind of like slightly organic-y forms of sulfur. So dimethyl sulfide, that's the molecule at the top, 2 methanes with a sulfur in the middle. And then carbonyl sulfide, which is this OCS molecule up here. So these are forms of basically gaseous sulfur that are formed by biological processes and then released into the atmosphere. And these turn out to be particularly important for climate. So we'll get onto those when we come to them. But to look at some of the fluxes and the stocks now. So most of the ultimate source of sulfur is ultimately from the lithosphere, and that's either through weathering or through volcanic emissions. Okay, and weathering is very easy for these minerals because basically, if there's any sulfate in rocks, that calcium sulfate is very, very soluble. Okay, it will just dissolve in water. I mean, it's unlike if you put a rock, like a granite, in some water, it'll just kind of stay there as granite for a long time. Whereas gypsum deposits, they will just dissolve in water. And rocks that have got pyrite in them, whenever those rocks get to the surface, whenever they get into that weathering zone, okay, they become oxidized rapidly, okay, because they're only stable, pyrite is only really stable in reducing conditions. So that acts as an easily weatherable source of sulfur, okay. So the flux there, 72 teragrams of sulfur a year, okay, quite high. I guess if you look right to the end of your kind of little pack of paper there, I've put a table of what these kind of actual thingies, teragrams or gigatons, or what they actually refer to in terms of actual amounts of stuff, which might be helpful to you. Okay, so that's the main sources for the lithosphere. So to get into the atmosphere, sulfur has to be either as a gaseous form, okay, so hydrogen sulfide or sulfur dioxide. So these are given off by volcanoes, or are given off, in the case of hydrogen sulfide, from sediments that are anoxic. So in kind of rice fields, bogs, marshes, those kind of regions, they can give off hydrogen sulfide. And then sulfate tends to form aerosols. So it's not necessarily gaseous, because it's got such a high boiling point once it reacts with water to form sulfuric acid. So that stuff kind of precipitates out as aerosols, and it's those aerosols which act at these cloud condensation nuclei. So the sources of these things, so dust, so bits of rock that have got sulfur on up into the atmosphere, but biogenic emissions of things like sulfur, hydrogen sulfide and sulfur dioxide, and volcanic emissions as well. So when a volcano erupts, the sulfur that's in those rocks tends to be in the gaseous form, and that just goes up into the atmosphere. Okay, so this is I think we've showed a picture very similar to this yesterday. So this is kind of an example. We're seeing dust, and some of that dust will have sulfur in it, and that will be kind of blowing into the atmosphere. It's got maybe a little bit of higher concentration or higher flux than phosphorus because sulfur is more abundant in the lithosphere. And then we've also got these biogenic sources. Okay, so any plant, okay, the organic material of that plant or even that animal, well, not necessarily be burning animals, but I guess there must be some animals burning in that forest fire, right? It's very, very sad for them. But that organic matter has got some sulfur in it, okay? And if you burn that, okay, that sulfur is going to go up into the atmosphere. Okay, so some of this, so there's biomass burning, so forest fires and stuff like that, are giving off sulfur into the atmosphere as it's released as the organic material is, in this case, rapidly oxidized. So there's also an emission of sulfur gases from the decomposition of organic matter. So this is just a pile of rotting waste. If you kind of smell some rotting waste, it smells a bit, funky. And some of that funky smell is this dimethyl sulfide and this carbonyl sulfide. Okay? So these gases, and I guess also maybe some hydrogen sulfide might be getting off this if it's decomposed enough in anoxic conditions. But these molecules are basically given off whenever there is any organic matter decay. Okay? And that doesn't have to be if like everything dies, but plants are constantly growing, constantly kind of shedding their leaves, constantly giving off like carbon back up into the environment, and they're constantly giving off these molecules back into the environment. So this also happens in the ocean. Okay, so when you have a big bloom of phytoplankton, that creates a lot of organic material. Okay, and not all that organic material is going to sink to the bottom or sink into the deep ocean before it decays. Some of that decay is going to happen in the surface ocean, and that decay is going to be producing these kind of sulfur-bearing gases. And those gases, because of Henry's law, will escape up into the atmosphere. So this is hard for you to see, so we'll make it dark. Ooh. So this is an image that I've stolen off the internet of the Smoky Mountains in America, and they're called the Smoky Mountains because they are kind of misty. Okay, and this is quite a common feature on like large forested regions. And what's happening here is that these forests, okay, particularly at night time when there's no photosynthesis going on, they're giving off a lot of these sulfur-bearing gases, carbonyl sulfide and dimethyl sulfide, because there's effectively decay of organic material going on. Okay, so these trees are producing these sulfur-bearing gases. That's not what we're seeing here. Okay, those sulfur-bearing gases get into the atmosphere and are quite rapidly oxidized from dimethyl sulfide into sulfur dioxide and methane, and then sulfur dioxide and CO2, and that sulfur dioxide then gets oxidized further to sulfate. Okay? So actually what we're seeing here is sulfate aerosol that's produced from gases which are then produced from the forests. And you can see the fact that's basically acting as cloud condensation nuclei. So actually what we're seeing here is the water that's condensed onto these droplets of sulfate, and that's what's causing the Smoky Mountains to be smoky. Okay? It's not actual smoke, it's just kind of low-lying cloud that's very persistent because the droplet size is very, very small because of all of these cloud condensation nuclei. Okay? So you can see that this happens on a larger scale than just a forest like this, and it's acting to make the forest, or in this case the albedo, whiter. So this is a dark forest, and if we put kind of like white clouds over it, the sun shining down on it will be bouncing back off into space again. Okay, so this is a feedback on climate in some ways, and we'll come on to that in a bit. Volcanic emissions, so volcanoes are full of sulfur. If you ever go to a volcano, like this somewhat cavalier attitude to volcanism, he's got a hat on, it's kind of not or any breathing apparatus. So this is giving out kind of lots and lots of sulfur-rich gases. You can see all the sulfur coming out of the volcano. So these are huge sources of sulfur into the atmosphere when a big volcano goes off. So this is the eruption of Mount Pinatubo, which is in the Philippines. So the images are Pinatubo, and you can see here that they are basically measuring the amount of sulfur in the atmosphere over the whole kind of atmosphere column depth. Okay, so these give out huge amounts in kind of one go of sulfur into the atmosphere, and that persists in the atmosphere for a while. The example up here of Tambora, I think I've got Tambora next. So this was a larger eruption than the Mount Pinatubo. So this was actually in Indonesia. It was Dutch East Indies at the time, but you know, stuff changes. And the impact of this was a dramatic global cooling. Okay, so the cooling wasn't uniform globally. So you can see here's a map reconstructed of surface temperatures in Europe in the year after the eruption. Okay, you can see Europe, particularly France, was a lot colder. So this led to the collapse of agriculture across Europe. So this is basically the price of bread and rye and stuff. Okay, you can see after the eruption that the prices of some of these things that were basically requiring lots of sunlight and kind of like warmth to grow, the price of these skyrocketed. Okay. It was also at this time that William Turner was kind of like painting all of these nice sunsets, and the reason for those sunsets was all of the sulfur in the atmosphere at the time, making it kind of all look nice, and his poor eyesight as well. I guess that was also helping. So there were lots of kind of, I guess, social and odd things that have been attributed to events like this. So when you have kind of like a dramatic change in the climate for a couple of years, that can have quite big social implications. So if you, I think some things have been tied to this, like the increase in the price of cereals, like bread and oats and stuff like that, led to feed for horses being really expensive. Yeah. So someone in Germany invented a bicycle. So the invention of the bicycle can be linked to the kind of the eruption of this volcano. Similarly, kind of other kind of food shortages caused in part by volcanic eruptions and sulfur into the atmosphere have been linked to kind of social unrest and things like that. So if people can't eat, they tend to overthrow their government. So I think it's a different volcanic eruption. Yeah, it's kind of true. So things like the French Revolution are thought to be kind of in the Great Reform Act at the same time in the UK, thought to be linked to some of these food shortages that were in partly volcanically induced. Okay. Anyway, so these are the sources that we've basically identified now. So we've got basically volcanic stuff blowing stuff into the atmosphere, which ultimately ends up being oxidized into sulfate. We've also got biogenic gases, so these are given off by decay of organic material, giving off these gases which then get oxidized into sulfate again. We've also got dust blowing up into the atmosphere and erosion and weathering of rocks. So these are the sources of sulfur. And just to point out that we've also added a little bit of our own, okay, by our fossil fuel burning. That's added this additional flux. So if you look at this, is a record of the acidity of an ice core. So this is basically measuring how much sulfate has been produced and then deposited on an ice sheet. And you can see that it's very, very spiky. Okay, and those spikes are individual large volcanic eruptions. But then superimposed on that spikiness, there's this kind of general upwards trend. Okay, looking at the red, that's sulfate. The bottom curve is nitrate, which is also given off by our anthropogenic activities, largely through our changes in agriculture. But you can see since the beginning of the 20th century, about here, we've been increasing the amount of sulfate in the atmosphere, increasing the acidity. And that comes from fossil fuels, which are, in some cases, particularly coal, particularly dirty coal, which is cheaper than clean coal, has got more sulfur in it, which is a fact. So this is this additional kind of extract of us basically increasing our weathering. Okay, that goes into the ocean. We don't really worry about that because the ocean has already got lots of sulfur in it. Not such a problem. But if we're pumping it into the atmosphere, you can see that the magnitude of our anthropogenic emissions are much, much larger than the natural sources, which is nice. Okay, so we're looking at now a combined, we've basically doubled the flux of sulfur into the ocean by our basically increasing weathering, and that can be mining, that can be changes of agriculture. Okay, let's increase that by 2. Now we've put a whole bunch of stuff up into the atmosphere. Okay, and because the atmosphere has a very short residence time, okay, it can't stay up there for very long. Okay, it means that there must be a corresponding outflux. Okay, otherwise the atmospheric concentration would go up and up and up and up and up. And because sulfate, because sulfur oxidizes to this sulfate form, that sulfate reacts with any water in the atmosphere, and the atmosphere's got a lot of water in it. That means that it forms sulfuric acid, which doesn't like being a gas. That basically condenses out into an aerosol, which means it falls out of the atmosphere. So this means that all of this sulfur that we put in the atmosphere is basically raining back down. Okay, so it's adding to a flux to the land surface and also into the ocean through deposition. Okay, so this summarizes our land cycle. So most of it's from mining. There are these atmospheric emissions, volcanoes, and biogenic emissions of sulfur. Okay, and most of it goes up and then it comes back down again. Okay, so it's only up there for a short amount of time. Okay, so there's no reason for this picture at all. It's just that, you know, it's quite cute. And sulfur smells, and he's got a nose. So we're going to look at the ocean sulfur cycle. So sulfur coming in from rivers, okay, and also being deposited from the atmosphere in the form of effectively acid rain. Okay, so that's falling into the ocean as well. So we've got this flux into the ocean, and we can now look at basically what's the residence time of the sulfur is in the ocean. So we know that the ocean has got lots and lots of sulfur in it because we can measure the concentration and it's quite high. So we can work out that there's this kind of, what is it, 1.2 billion teragrams of sulfur. Okay, so whatever, there's no way of saying that without it being big. Okay, that's an extremely large number of an extremely high amount, like teragrams, 10 to the 12 grams, so lots. Okay, and our flux in is still teragrams, but only 150. Okay, so what we can do is we can work out the residence time, and the residence time is the stock of stuff divided by the flux. Okay, so in this case, 1.2 billion divided by 150. So this is 10 million years. So that means that if we stopped the flux into the ocean and we only had the out fluxes, it would take 10 million years for the concentration of sulfur in the ocean to reduce by half. Okay, so it's very, very hard to change the concentration of sulfur or the amount of sulfur in the ocean. Okay, so this means that, so if we look at kind of profiles of concentration down into the ocean, if we look at elements like phosphorus and nitrogen, okay, in the surface ocean, life uses up those elements. Okay, it takes them out of the dissolved phase, okay, puts it into organic matter, which then sinks down into the deep ocean. So that means that the surface ocean is really, really depleted in those elements. Okay? And then the deep ocean gets enriched in those elements as that organic material is remineralized or respired or dissolved back into the available phase. Now, with sulfur, those processes are still happening. It's still being used in the surface ocean and added to the deep ocean, but the rates of those uptake and removal are so low compared to the residence time that the concentration profile looks like this. Okay? The change is so small in the surface ocean and so small in the deep ocean, it's not measurable. Okay? So there are differences in concentration because if you evaporate a bit of the ocean, okay, you make it more salty, you'll increase the sulfur concentration because you're basically just adding or taking away water as you precipitate, as you rain into the ocean. But the overall content of the ocean will stay constant for sulfur. So it's basically, we've got these terms of biolimiting, biointermediate, so things like carbon, so that varies a little bit down with the water column, and bioinert. So bioinert doesn't mean they're not essential for life. Okay? It just means that their concentrations are not affected by life because there's so much of them in the ocean. So things like sodium, magnesium, potassium, these are all needed. Life needs these things. Without these things, life would be pretty miserable or non-existent. Sulfur is one of these elements. Okay, so it's always present. Yeah, it's like the rice at the all-you-can-eat buffet, right? It's always there. There's always loads and loads and loads of it. It never gets used up. Okay. Okay, so we look at some output fluxes now. So we've got all of these, I guess, inputs. We've got rivers coming in. We've got some deposition from the atmosphere. We might have some volcanoes in the ocean that are giving stuff out into the atmosphere as well, but that's not what we're on about. We have these biogenic emissions. So just like on land, if there's any organic material, particularly in the surface ocean, that's going to produce some dimethyl sulfide as it decays. And that, because if you increase the concentration of a gas in the water, okay, some of that gas will diffuse up into the atmosphere until the concentrations are kind of, the ratio of the concentrations is equal to the solubility constant via Henry's law. So there'll be a flux out, okay, of the ocean. By that way. So this is this dimethyl sulfide. So it's produced by decay of plankton. And actually, because the rates of production and basically the rate of growth and decay is quite high in the ocean compared to on land, because like the organisms are just single cell things. This stuff can be produced quite quickly, and if you produce it in the water, okay, some of that is going to want to diffuse up into the atmosphere until the concentrations are equal to the solubility product. Okay, once it gets there, okay, this is this dimethyl sulfide, which is that molecule up there. If you add oxygen to that, and there's lots of oxygen in the atmosphere, which is, you know, pretty good, that produces sulfur dioxide and CO2. That then further gets oxidized to sulfate. And that sulfate is the thing that can act as a cloud condensation nuclei. So there's this idea that there's this biological regulation of climate through this emission of sulfur. So if you get this increase in warming, if it gets warmer for some reason, that means that we'll have more photosynthetic activity, because it's a chemical reaction. It'll happen faster. We'll have more biological activity. That'll produce more biomass, and also the rates of decay, the decomposition will be higher, okay, because it's warmer, so we get more decomposition. It's like leaving your like lunch out of the fridge. It kind of like heats up and decays and tastes awful. So if we increase those, then we're going to increase the rate of production of these sulfur gases, of dimethyl sulfide and carbonyl sulfide. And that will increase this cooling effect. So imagine this is not a volcano, but if this is kind of biological activity giving off more sulfur, okay, because it's warmer, that sulfur gets into the atmosphere and then cools the planet through this radiative forcing. So this is this idea of it's a negative feedback. So we warm the ocean, we get more plankton, we produce more dimethyl sulfide. That dimethyl sulfide gets into the atmosphere, oxidizes, forms these cloud condensation nuclei, which then cool the planet, which kind of reduces this. Okay, so it's kind of like a little savior to save us from global warming. Or is it? Okay, so this hypothesis was initially called the Core Hypothesis, because everyone likes an acronym. It was by these guys, Charleston, Lovelock, and whatnot. So James Lovelock is the author of the Gaia Hypothesis, which is kind of a bit of a hippie Bible, which is kind of like the Earth is considered as a living being that can regulate its own habitability. So once Gaia, the Earth, has kind of established itself, it will always strive to maintain kind of change processes will happen which will maintain the habitability. So things like maintaining water as a liquid on the Earth's surface, keeping the climate within some tolerable bounds. The idea is that the Earth is somehow sentiently doing this. Bit of a nutter, but anyway. It's a very good book. So this idea of the Core Hypothesis was this process acts to kind of stop kind of global warming, or at least mitigate it. But then, of course, there's the anti-Core Hypothesis, which actually, if the ocean warms, we might decrease the amount of plankton. Okay? And the reason for this is that plankton doesn't just grow because it's nice and warm and it can multiply when it's nice and warm and there's lots of light and carbon dioxide. It also needs the other nutrients. Okay? It needs nitrate and phosphate. Okay? And the major supply of nitrate and phosphate to the surface ocean is from the deep ocean. Okay? This process of upwelling, but mixing between the surface and the deep ocean. Now, if you make the ocean warmer, particularly if you make the surface ocean warmer, that makes the surface layer more buoyant. Okay? So it's harder to mix water that's got lots of nutrients from the bottom up to the surface. Okay? So if warming the ocean actually decreases phytoplankton growth, it means we'll have less dimethyl sulfide, and this cooling effect from clouds will become less. So this is this idea that actually it works the other way around. And whichever one of these happens depends critically on the effect of ocean warming on phytoplankton growth. So if you warm the ocean on average, will we get more or less primary productivity? And this is a big unanswered question, okay, because it depends both on kind of rates of biological activity, which is one this is kind of driving for, or availability of nutrients and limitation through ocean stratification. Okay? So understanding these processes of how nutrients move between these reservoirs is really important, because they determine whether it's going to be really bad or slightly less as bad. And the next one is ooh the claw, which is probably a reference you're too young to, yes. Okay, so now we're going to think about removing this stuff from the ocean. So how does this stuff actually get out? So one method is we're basically putting lots of sulfur into the ocean, so the concentration is very, very high. Okay. Now, I don't know if anyone's been to the ocean near Scotland. It's kind of like this. It's kind of wavy. I don't think this is actually a picture of Scotland, but let's just say it is. So each of these little droplets of water, okay, has got some sulfur dissolved in it. It's got all of the other nutrients and stuff like that dissolved in it, but because the concentration of sulfur is so high in the water, it's actually got quite a lot of sulfur in it. It's also got sodium and chlorine and all that kind of stuff. So when those droplets kind of like made in the surface of the ocean, some of them actually get blown up high into the atmosphere, okay, and I guess particularly, I mean, if you've been to, if you go to Portobello to go to the beach, which is, you know, a thing you could do, and you lick the buildings, I don't lick the buildings, they'll taste a little bit salty, I imagine. I just don't go around licking buildings, that's weird. And that's because salt is being transported from the ocean and being basically sprayed onto the land, this kind of salty, yeah, so it's being sprayed, and it's also, if it gets high up into the atmosphere, it can actually be transported a very, very long way, okay? And it comes out either when it rains, so raindrops may form around these kind of little salt crystals, or it may just fall out of the atmosphere as dry deposition, as kind of salty dust. So that's in some regions of particularly the terrestrial biosphere, this is a major source of nutrients, particularly sulfate, which for instance in rainforests where weathering is actually very low, the addition of nutrients, particularly sulfate, through this process is actually very important. Okay. We also take sulfur out by forming sulfur minerals. So this can happen in deep sea sediments where the oxygen is removed through respiration. Okay, and we can start to form minerals like pyrite. Or as seawater is kind of like cycled through hydrothermal systems that can reduce the sulfur and form pyrite as a hydrothermal alteration. Okay. So sulfur is bioinert, although that doesn't mean it's not involved in biology. It means its concentration is near invariant in the ocean. Some main sources, mostly from the rivers. And this dimethyl sulfide, this feedback between the sulfur cycle and the climate is really important. And really understanding how nutrients control biological productivity is key to how this basically cooling mechanism will behave in the future. Okay, so the biosphere, it basically forms these kind of important parts of it. Okay, and when organic matter decays, we form hydrogen sulfide. So I've already showed you this slide, I think, in the nitrogen lecture. But just like nitrate, if we've got lots of organic carbon and we run out of oxygen, okay. So if we want to take our pointer options, if we want to take organic carbon in this kind of form here, we'll add oxygen to it to form CO2, and bacteria can get energy out of that. Okay, but if we've run out of oxygen, okay, as we go down into a sediment, we might use up all the oxygen, and we will start using the nitrate, and then we might run out of nitrate and use iron and manganese. But ultimately, we might get down to using sulfur. Okay, and particularly in marine sediments, there's so much sulfur available because the pool water has got all this basically ocean water in it, so it's got really high sulfur concentrations. We're able to get a small amount of energy by using the sulfur, okay, to oxidize the organic matter and produce kind of a dissolved, well, this is a CO2 species, basically, a dissolved inorganic carbon, and hydrogen sulfide. Okay. So if you've got anoxic sediments, okay, they quite often have got a lot of hydrogen sulfide in them. So this is kind of, if you get some really deep, some really black, horrible mud from the bottom of a lake, if you kind of scoop it up, if you smell it, it will smell awful because this molecule is bad smelling. Okay, so this is the kind of thing that you might see in a profile of concentrations as you go down from the surface of the sediment to the bottom, as we start out with lots of carbon and then it gets respired. Okay, and we can see that the oxygen concentration will go down. Okay, but in the deep parts of the sediment, we might get quite high concentrations of hydrogen sulfide. Okay. So this is, again, so this environment's kind of like this up here. In boggy kind of places, we are effectively producing emissions of hydrogen sulfide through the decay of organic matter and use of any sulfate in the system as an oxidizing agent. Okay? And this is important because this is a gaseous species which can get into the atmosphere, okay, and immediately oxidize to sulfate or sulfur dioxide and then sulfate. So this process of basically emissions from wetlands, but also our emissions from anthropogenic burning and all that kind of stuff, this is producing sulfuric acid as these molecules get up into the atmosphere. So that kind of concludes the natural cycles, okay, so sources, the transits, things like that. You've got this thing written down, so I'm not going to go through it. There's an important link between sulfur and climate. So every time we're increasing our sulfur emissions to the atmosphere, either through volcanoes or through biogenic emissions or through, I guess, the hydrogen sulfide out of wetlands, okay, that's going to act as a cooling. And critically, basically, the more sulfur we put in the atmosphere, the more acid rain we're going to get. So this is just a plot to show the cooling effect. So this is the estimate of basically the temperature or the radiative forcing change due to all of our activities that we've done. So we've burnt lots of fossil fuels, lots of CO2. That's caused a radiative forcing to make the planet warmer, just like methane and CFCs are acting as greenhouse gases. But it's this one here, the sulfate. So the sulfate emissions are really what's causing we basically are acting as a mitigation of some of this effect up here. One of the other things on this plot is you'll notice that there's a very, very small bar here, a red one, okay, for sulfate. So sulfate causes cooling through these atmospheric aerosols reflecting right back into space. But if you look at this one here, so the effect of ammonia is also a cooling, okay? But sulfate is having an effect on the ammonia in the atmosphere. Okay, so ammonia goes into the atmosphere, it basically will oxidize. That oxidization will take it to nitric acid, which acts in a very similar way to sulfate in its aerosol effect. But there's a small effect here on the ammonia. So we'll just hopefully look into that in a bit. So we're putting stuff into the atmosphere. It's going up there and it's coming down forming acid rain. Yeah, so looking at through time, we've basically increased our emissions of sulfur into the atmosphere. So most of this is through fossil fuel burning, and that's also adding nitrous oxides. Okay, so we're adding sulfuric acid and nitric acid to the atmosphere. Okay, and these are causing acid rain. So that's these bars here. So this is not acid rainness, but this is the radiative effect of having these acids in the atmosphere is to act as a radiative cooling through forming more clouds. But they're both also causing acid rain. Okay, so this is the kind of the effect of that. So this is a building that was built somewhere in Germany in 1702, and in 1908 it kind of looked like this, and you could see her face. Okay, and then like 60 years later, her face is gone. Okay, and this is because of the local effects of this acid rain. And this is kind of a map of the pH of rainfall. So in the 80s, so we were basically burning lots of fossil fuels in Western Europe, particularly in the UK and in Germany. And that's causing the addition of this sulfate and nitrate, okay, is basically locally raining out because we're putting so much in the atmosphere, okay? It's just raining out as acid rain and causing kind of lots of problems over these regions, dissolving their buildings, and also having effects on the biosphere in there. So I'll just go over and explain this, that little difference, that effect of sulfate on the ammonia effect on clouds is that if you have ammonia in the atmosphere and you have sulfuric acid in the atmosphere, those two will react together, okay, and form ammonium sulfate. Okay? Now this means that it's basically, one's an acid, one's a base, they're effectively neutralizing each other. So the effect of having more sulfate in the atmosphere is actually to reduce the impact of having ammonia in the atmosphere. Okay? So this is also important in terms of understanding that tiny little bit of radiative forcing, but it's also important because ammonium sulfate is effectively a fertilizer. I mean, we actually make it and use it as fertilizer. Okay? It's a nice replacement for ammonium nitrate, because you can make bombs out of ammonium nitrate. You can't make bombs out of ammonium sulfate. So actually, this reaction that happens in the atmosphere is actually a very useful kind of transport vector of basically natural fertilizers. Natural, I mean, they're made by us putting our anthropogenic emissions to the atmosphere. And it can be basically rained out as kind of fertilizer over the land, adding basically nitrate to the soil, which is pretty nice. There's also an interaction with the phosphorus cycle. So if we have acid rain, okay, that's going to rain out onto the soil, onto trees and stuff and whatnot, and it's going to lower the pH of the soil. Okay, if we lower the pH of the soil, if our region is reliant on there being kind of phosphorus available because we're at a neutral pH, if we add acid rain, we are going to lower the pH of the soil and we're going to remove some of the phosphate from the available pool. Okay, so one of the reasons why acid rain is such a problem in kind of in terms of its effect on the terrestrial biosphere, so particularly on forests in Scandinavia and places like that, mostly Scandinavia, is that the acid rain wasn't actually harmful in itself. Okay, it didn't like dissolve the trees away, but it removed some of the phosphorus from the available pool, so the trees didn't have enough nutrients to grow. Okay. It also has an effect on other element cycles, so it can also have effect on the mobility of some pollutants and contaminants in the land. So if you've got some contaminated land that's got lots of cadmium all over it, or some lead or something like that, it might be fine, all the pollutants might be fine just sitting there in the soil, but then if you dump a load of acid rain on it, it might start leaching those toxic elements out and into the wider environment. So you can see here that the sulfur cycle is having an impact on other nutrient cycles, the nitrogen cycle or the phosphate cycle. Yeah, they also interact on weathering. So, I mean, if you add more acid to the atmosphere, you're going to dissolve rocks more. That dissolving rocks will provide more nutrients. So the interaction isn't quite as simple as, one thing is bad, that will reduce the nutrients. In some cases, it might actually increase the availability of nutrients. It depends on what the initial soil pH was and all kinds of things like that. So it affects lots of things. So I don't think anybody is expecting you to kind of like write down or remember all of this diagram, but it's just really to show that all of these systems, so the nitrogen cycle, the carbon cycle, the sulfur cycle, you could add another thing on here for the phosphorus cycle, and that you can see that they are actually all interlinked and dependent on each other. Okay, and that's really important, that just understanding one of them is not enough. You have to understand the interplay of one on the other, which is quite nice. So to conclude, the whole kind of nutrients kind of cycly thing, there are different types of elemental or nutrient cycles, ones that have gases, ones that have are dominated by sedimentary and aqueous cycling. And I guess for almost all of them, in fact for all of them, the largest stock, okay, the largest reservoir of all of the elements is the lithosphere. So understanding how geology works and how geology makes available these nutrients and these elements critical for life is really important. But these geological processes are quite slow. Okay, so if you're interested on how the biosphere might respond on a more rapid kind of timescale, or more climate change kind of timescale, we have to look at the kind of the processes that are happening in the ocean, in the atmosphere and in the soils. I think one of the other things that's really important to get from this lecture series is that quite a lot of these chemical reactions, okay, so take for instance the nitrogen cycle, okay, you can't do any of the, like all of the steps in that nitrogen cycle without biology. So not only is biology relying on the nitrogen cycle would not happen without the biology. So the nitrogen fixation would only be lightning, okay, if we didn't have the biological nitrogen fixation, which is responsible for most of the natural fixation of nitrate, or fixation of ammonia, and which then gets kind of cycled through the biological system and becomes nitrate. We wouldn't have nitrification, we wouldn't have denitrification. These reactions may happen inorganically, but they are made much, much more efficient by these microbial processes. Okay? And the microbial process is also important for the things like the sulfur cycle through the degradation to produce these kind of dimethyl sulfide, or using an oxidizing agent in sediments to produce hydrogen sulfide. So biology is important for nutrients, and nutrients are important for biology. It's like a special relationship. Also with every one of the nutrient cyclings, and probably with every one of every element cycling within the Earth system, anthropogenic perturbations are really, really quite dominant now. So we're basically in an entirely Anthropocene world, which is exciting. Okay, so that's the lecture series done for now. So here are this table, which should be useful to you. So most of the things I think were gigatons of carbon and teragrams of stuff converted between those. Did I talk about the lecture thingy? Not the lecture, the exams. So the exam